Welcome to the session on Faraday's law and transforming EMF. In this session, we shall be discussing the fundamental law, which is Faraday's law, which forms the basis for first Maxwell equation. I just want to remind you once again, Maxwell's equations are the backbone for all modern day wireless communications. Maxwell's equations are 4 in number. They can be expressed in integral form as well as in differential form. Well, the first Maxwell equation is based on Faraday's law. Now, in this session, we shall be discussing what is Faraday's law as applicable for a wireless communication engineer. Now, in addition to that, we also complement this discussion with what is called as transformer EMF, how it is related to Faraday's law. Now, let's enter into the session. Now, historically speaking, it dates back to 1820, almost 200 years back. A physicist by the name Ørsted was performing experiments in his laboratory. It was an accidental observation. What he observed that there was a compass, magnetic compass, and what he noticed that there was some flow of electric current in the vicinity, and this magnetic compass, the needle of the magnetic compass, started deflecting. So he concluded that an electric current gives rise to magnetic field. So what he noticed, there was a flow of current. Due to that, there was some magnetic field that was produced, and that magnetic field was responsible for deflecting the needle of the magnetic compass. That means he has observed a relation between the electric current and the magnetic field. Now, how it is related to our discussion is that there are two types of domains, especially in this field theory. Our subject is electromagnetic fields. In this field theory, there are two types of domains broadly: static domain and dynamic domain. Static domain means the electric field is static electric field, which is electrostatics, and the magnetic field is static magnetic field, which is magnetostatics. As long as you are in the static domain, the fields are independent of each other. I repeat, in static domain, the fields are independent of each other, which means a static electric field is in no way connected to static magnetic field. Whereas if we come to the dynamic domain, which is also referred as time varying domain. Static means time invariant, dynamic means time varying. So it is time varying domain. In time varying domain, the same fields, namely electric field, which is electrodynamic field, magnetic field, which is dynamic field, so magnetodynamic field, these two fields are interdependent on each other. Previously it was independent of each other, now it is interdependent of each other. One depends on the other mutually. That time varying electric field is dependent on time varying magnetic field, and time varying magnetic field is dependent on electric field, which is the vice versa. Now, there is a link between the two fields in the dynamic domain. We started with what do you say this as Ørsted observation, which happened in 1820. Exactly 10 years later, roughly around 1830s, Faraday, who is the topic of today's discussion, Michael Faraday, has observed the vice versa of that. He says that if you move a conductor in the presence of time varying magnetic field, or I can say a moving conductor in the presence of magnetic field, or a static conductor in the presence of steady magnetic field or static magnetic field, in either ways you get electric current that is produced. So who is the source? Magnetic field. What we are doing? Placing a conductor in the presence of time varying magnetic field. What do you get? you get electric current. What Oersted observed? Flow of current has led to magnetic field. What Faraday says after 10 years? The reverse of this, the vice versa of that. Current leads to magnetic field. Faraday says magnetic field gives rise to current, because you are placing conductor in the presence of magnetic field, and due to magnetic field we are getting current. Of course, it's not so simple and straightforward as we say. The magnetic field in which the conductor is placed, it has to be time varying magnetic field. It's not just magnetic field, it is time varying magnetic field that will produce the current. Of course, there are some deeper insights in that. We are just discussing on the surface. Now, 4 years later, another engineer by the name Lenz, which is known as Lenz law, he also made some valuable insight, experimental observation out of this. So together, Oersted, Faraday and Lenz has contributed for this mathematical discussion what we are going to see now. I am just referring to the historical perspective of this Faraday's law and transform EMF. Now we enter into the mathematical discussion, quantitative way. We try to understand this. Now, starting with E equal to N d phi by dt. Let us decode it, what it stands for. E is the EMF. What is EMF? Electromotive force. The force which motivates the electrons. What will happen if electrons are motivated and they move? Flow of electrons, which we say as electric current. Movement of electric charges will constitute electric current. So what will happen due to EMF? What results is electric current. Now, here N stands for number of turns. You are placing a conductor in the presence of magnetic field, isn't it? That conductor will have certain turns, number of turns. Now, phi. Psi means electric flux. Phi means magnetic flux. D by dt of phi means, d by dt means rate of change in flux. It simply means change in flux. D by dt of phi will tell you how much that change is there. So phi means flux. D by dt of phi means what is the change in flux? How much is the change in flux? What does it amount to? You just forget about this N, keep it aside. On the right hand side you have d by dt of phi, left hand side you have E. What does it mean? EMF will result due to rate of change in magnetic flux. If you place, N stands for number of turns of the conductor. If you have a conductor with N turns and if you place it in the presence of magnetic field cannot be visually seen with our eyes. Will represent in the form of lines of force that we say as magnetic flux. So here indirectly we are speaking to magnetic field. So if you have a conductor with N number of turns and if you place it in the presence of magnetic field whose equivalent magnetic flux is phi and d by dt of phi, and that magnetic flux happen to be changing with time, then what will happen? Then this will happen. EMF will result. So E is due to d by dt of phi, and N stands for number of turns. More the number of turns, more the EMF that can be induced. Now let us for simplicity say the number of turns in the conductor is 1. So N equal to 1. Then this equation will become E equal to minus d phi by dt. EMF induced in a conductor is due to the rate of change in the magnetic flux. Now, what does this negative sign refer to? It is nothing but observation of contribution of Lenz. What Lenz has observed is that, now try to understand this way, there is a magnetic field here. That magnetic field is represented in the form of magnetic lines of force. In that magnetic field you are placing a conductor. This magnetic field is not static magnetic field. That magnetic field is changing with time. So, that magnetic flux is also changing with time. Because it is changing with time, we are saying d phi by dt. Change in flux with respect to change in time. dt, nothing but. Now, in that presence, you are placing a conductor. Now, what will happen? EMF is induced in the conductor. What EMF will do? Electromotive force. Force which motivates the electrons. Nothing but movement of charge, electric charge, electrons. It will lead to current. What current will lead to? What will happen if current is flowing in a conductor? It is surrounded by magnetic field. See where the story started? With magnetic field. Where the story ends? With magnetic field. I repeat this sequence once again. You have some certain magnetic field, that is a time varying magnetic field. So you have time varying magnetic flux. So the story starts with magnetic field. You are placing a conductor in that. Because you are placing a conductor in the presence of time varying magnetic field, the time varying magnetic field will link to the conductor. As a result of change in flux linking to the conductor, that is d phi, change in flux with respect to change in time, change in flux linking to the conductor, you get EMF. Because of EMF, you get current flow in the conductor. Because of flow of current in the conductor, you get magnetic field. So it starts with magnetic field and it ends with magnetic field. Now the thing is that the actual magnetic field in which the conductor is being placed, that is called as primary magnetic field. At the end, you are getting another magnetic field, that is called as secondary magnetic field. So this is the source, this is the result. This is primary, this is secondary. Both are magnetic fields, but the direction of current that is produced, which is producing this magnetic field, the direction of current is opposite to this. That means whatever secondary magnetic field that has been produced due to the current, that will oppose the primary magnetic field. So hence we use this negative sign, opposing. On one side you have EMF, which is giving rise to current and giving rise to magnetic field. That is minus of this magnetic field. That means the primary magnetic field and secondary magnetic field will oppose each other. That is the meaning of this negative sign. Now moving forward. Now if we go back to our basics of unit 1, where you have seen electric potential, you have a very famous equation. What is that? V equal to E dot dl. Of course, we use minus and plus alternatively depending on the direction of the electric field. Whether work is done against the electric field or whether work is done along the direction of the electric field. Depending on we use plus or minus. Now, in place of V, we have E. What is unit of voltage? Volts. What is unit of EMF? Volts. So, according to this context, means contextually, in place of V, I am taking just E. Because both will do the same thing. When you apply voltage, it leads to current. When EMF is induced, it leads to current. But the context is different. So I am taking, in first unit we have written V equal to integral E dot dl. Here I am writing E equal to integral E dot dl. That's the only difference. And the EMF is induced in a closed conductor, in a closed path. So that's why I am using the symbol, closed contour symbol. Keep this aside. This is one relation. Now, this is about E. Now bother about phi. About phi we have seen in unit 2, magnetostatics. What is phi? Magnetic flux. How do you express magnetic flux? Magnetic flux is obtained by integrating flux density. If you integrate magnetic flux density, you get magnetic flux. If you integrate power spectral density, you get power. If you integrate charge density, you get charge. Similarly, if you integrate magnetic flux density, you get magnetic flux. Why I am taking magnetic flux density? Because you are placing a conductor, a closed conductor in the presence of magnetic field. So you have some area which is enclosed by this closed path. What is the amount of magnetic flux linking to this area? So flux linking to this area, flux density. That's why you are establishing the relation between phi and B. Now, what we have here, E equal to d by dt of phi. So E equal to d by dt of course it is minus d by dt of phi. In place of phi, take integral b bar dot ds. Okay. Now, here you have derivative of the integral, derivative of the flux density. Be very careful. Here you have, of course it is time derivative, d by dt. If it is d by dx, it is space coordinate, x, y, z are called space coordinate. That is called space derivative. Here we have d by dt, time derivative. So essentially you have a derivative of integral. What is this integral? Surface integral. What is the surface? Inside this closed path of the conductor, you have some surface. That surface. So derivative of the surface, derivative of the B. Is the conductor changing again and again? Are you changing the conductor again and again? No. It is fixed. You are selecting a particular conductor, closed conductor. So this surface area is constant. So the surface for which you are considering integral will be constant. Now derivative of B is remaining. So you are neglecting this, but you are only considering this. The derivative is performed only for this. So since you are performing derivative only for that, that is called as partial derivative. You are doing the derivative partially. That means D becomes dou. For that, you have to take the derivative inside because you don't want to derive You no more want to derive this surface because that is fixed, happens to be fixed. So take this inside. It becomes, if it goes inside, it becomes dou. So it will be minus surface integral dou b by dou t. That's what we find here. On the left hand side, what do you have? Integral e bar dot dl. Integral e bar dot dl. On the right hand side, what do you have? We are taking this d by dt inside, it becomes dou b by dou t. Surface integral dou b by dou t ds. Now in the right side you have ds, surface integral. On the left side it is dl, that means it will be line integral. Of course it is a closed line integral, but basically it's a line integral. Left side you have line integral, right side you have surface integral. To make uniform integrals, convert left hand side also into surface integral. Why? Because here in the left hand side you don't have a line, it is a closed line. Inside a closed line you have surface. So it is possible to convert the left hand side closed path into open surface. So that here also you have surface, left hand side also you get surface. Now what we have to do, our objective is to convert the closed line integral in the left hand side into surface integral. Now there are theorems, Gauss divergence theorem, Stokes theorem, Lines theorem. Which theorem you use to convert line to surface integral? Yes, Stokes theorem. Stokes theorem converts line integral into closed line integral into surface integral. So what Stokes theorem says? It should not be closed surface, it should be open surface. So the closed line integral of any vector can be equivalently written as the surface integral of curl of that vector. That means E bar. So E bar. This is called Stokes theorem statement. That will be equal to, right hand side will be same. Now you have surface integral, right hand side, left hand side. You have ds, ds. So what I have written here? So here you have del cross surface integral ds, surface integral ds. So you have del cross E bar equal to minus dou b by dou t. What do you mean? Make a statement out of this? The curl of the electric field vector is equal to the rate of decrease. D by dt means rate of change. Minus d by dt means rate of decrease. Plus d by dt means rate of increase. So is equal to dou by dou t minus. So rate of decrease in the magnetic flux density vector. This is known as transformer EMF. Why I am saying EMF? Because what is this left hand side equal to? E dot dl. We have started from here. What is this E dot dl equal to? This E dot dl is nothing but EMF. So essentially we have written an expression for EMF. That's why I am saying EMF. But why transformer EMF? See, there are two types. Transformer EMF, generator EMF. Out of curiosity, I have written generator EMF also here to understand. Just out of curiosity. Now, what is the principle of generator? Let us say hydel power generation. Hydroelectric power generation is happening. Hydel power generation. What happens? There will be big turbines, isn't it? Big turbines. So what will happen? When water falls on the turbine will move. Hydel means water. Let us take the example. When water falls on the turbine will move. Where the turbine is moving? In between two magnets. There are two big magnets. Because there are two big magnets, in between there is magnetic field. So where the turbine is moving? In the presence of magnetic field. So the conductor is moving, but the magnetic field is static. Why I am saying static? Because there are two magnets. Due to magnets you get steady magnetic field or static magnetic field. Magnets are fixed. You have static magnetic field. There is no change in the magnetic field, but there is movement in the conductor. A moving conductor in the presence of magnetic field. You are getting EMF induced in this case also. What Faraday says is that either the conductor has to move in the presence of magnetic field, then the magnetic field can be static. If the magnetic field is static, then the conductor has to move. If the conductor is not moving, if it is static, then the magnetic field should be time varying magnetic field. If both are moving, it's okay, fine. If magnetic field is varying with time, conductor is also moving, then that is fantastic. You get two types of EMFs, transformer EMF, generator EMF. But to get EMF, essentially, the conductor has to be moving in the presence of steady magnetic field, or the time varying magnetic field should be there if the conductor is static. In generator, between two magnets you have steady magnetic field. Magnetic field is steady, but conductor is moving. So that's called generator EMF. In transformer EMF, there is opposite. You know the principle of transformer. There are two coils, primary coil, secondary coil. The coils do not move. The conducting coils do not move. But the current that is flowing in the coils, the voltage that is applied is time varying. You have time varying current. As a result, time varying magnetic field. But conductor is static in transformer. Two coils, primary and secondary coil, they are fixed. Conductors do not change. Conducting coils do not change. There is time varying magnetic field. So here that is happening. There is rate of change of magnetic field. Magnetic field is changing. Conductor is not moving, which is the principle of transformer. So I am saying transformer EMF. Suppose if you have a moving conductor, steady magnetic field. Moving conductor means, then in the case of E dot dl, we have to take EM because there is motion of conductor. M stands for motional aspect. In place of E dot dl, here we write EM dot dl. E is replaced with EM. Now what is the expression equal to? Electric field is, by definition, the amount of electric force exerted on unit electric charge. Electric field is the amount of electric force exerted on unit electric charge. If I take EM, then it will be FM. What is FM? The formula we have seen in the previous discussions. FM is QV cross B bar. Charge Q moving with a velocity V in the presence of magnetic field B bar. And why I am taking cross product here? Cross product of two vectors will be a vector. Force is a vector. So you have to use here cross. What happens if you take dot here? Dot product of two vectors will be scalar, but force is not scalar. So you have to use essentially cross. Now EM is F by Q. This is F by Q. Q cancels. What remains? V bar cross B bar remains. So in place of EM, V bar cross EM dot dl. This is generator EMF. So this is all about the Faraday's law, observations of Oersted, Michael Faraday and Lenz, and the two types of EMFs. One is transformer EMF and the second one is generator EMF. With this, we conclude this session.